Okay. So welcome this morning. We'll have a long talk about control of soft robots in a generalized sense, I would say. And you will see that I will mainly base my presentation on what I've been working for quite many years, namely modeling and control of robots with elastic joints. I will then cover also the extension to variable stiffness and to several control problems related to this class of soft robots. As you see, I just changed a bit the title of my presentation. So it's control of soft robots. You will hear a lot of control methods, actually. But I'm focusing on regulation, on trajectory tracking based on feedback linearization. And then we'll see how all these things can be used, for instance, for addressing some special problem in the collision detection area, including the fact that, I don't know if I will have time to go there, but including the fact that when you have safety in human-robot interaction, you typically want to impose some reaction to the robot when the robot discovers that there is a collision or some closeness to collision. And in that case, you would like not to bias the robot reaction due to the presence of gravity. So you would like to let the robot float in absence of gravity. So gravity cancellation is another interesting control topic per se, and in particular for this application. And as you may suspect, it is not that easy to achieve perfect gravity compensation or cancellation, I would say, when you're moving a flexible device, okay? So we will see also this type of things. So this is the outline, more or less what I've said before. And no? It's okay. Okay, good. So I will start with a few motivation, but of course I don't think I need to motivate you for addressing these issues. Then we will go really like in a textbook, I would say like in a robotics handbook, and I'm quoting the Springer handbook on purpose, on the simple step in dynamic modeling of robots, mainly addressing the issue of what assumptions are beyond these models. And then with the model at hand, we will address inverse dynamics, which is one classical aspect, computing the torque needed to do some motion. And then how we convert this into feedback mode. So we need some sensorization, and we need to close the loop for regulation tasks in the presence of gravity in particular. And we will see 2 or 3 types of simple law. And then when you address the more challenging issue of following a trajectory and recovering from disturbance and errors, then we will use the feedback linearization design technique. So all this, in a sense, generalized what you already should know, and I guess you know it well, for rigid robots. So from, let's say, Siciliano Sciavico book, textbook, okay, to the case of elasticity and flexibilities. So having presented this for the joint elastic case, I will then extend to robots with variable stiffness. In particular, there we are interested in controlling not just motion, but also stiffness, as we mentioned already. So how feedback linearization can be used, and if it can be used for doing simultaneous and decoupled control of motion of the links and stiffness of the joints. We will address this for a single device, but we will see that the extension is pretty much straightforward to multi-degrees of freedom, provided that you have a good model. And then I will conclude with this perfect cancellation of gravity, and then some example of use of these techniques for collision detection and reaction, actually. Okay, motivation. Why do we address flexibility, and in particular flexibility in the transmission? Well, in industrial conventional robots, which are massive, the first thing that it's compliant is the transmission. So if you have long shaft, like in the traditional Puma arm, where you have the motors mounted on the elbow and the 3 motors drive the last 3 joints, so you have this long shaft and they are subject to torsion. And you can model this torsion as a concentrated torsional spring, in fact. Or if you're using harmonic drives, which are inline, compact, large reduction ratio transmission, and they are intrinsically flexible because of the construction, the fact that they have a different number of teeth on the inner and outer gears, so they introduce this kind of flexibility. However, and this is our stuff now, there has been an intentional introduction of flexibility. So, for instance, up to some years ago, this harmonic drive stuff was something that you would like to have because you have reduction ratio of 150 to 100 with relatively low dissipation of power. And so you can have a small motor driving heavy links, but you have to live with this kind of vibration induced by the flexibility of these joints. So a completely different story is when you introduce on purpose, like in the serial elastic actuation and in whatever you have heard so far here. And there are several reasons for doing this. Here I'm mentioning only safety, but as you know, there are also performance and energy aspects which are very important. So how this is introduced in this type? Well, here I list some examples, including variable stiffness actuation, or, for instance, a device developed in Stanford, so a redundant macro-micro or parallel actuation device where you can have still two motors for moving a joint, but one motor is located at the base with a transmission, and then a small motor at the joint which correct the flexibility induced by the transmission, and things like that. Or when you have relocation of the actuation, just because you want to improve the dynamic performance of your mechanical design, and then you have cables and pulleys transmitting motion from the actuators to the driven joints, and of course these are flexible. So all these phenomena, of course, they are distributed in nature, most of them, but you can reasonably model them as a concentrated elasticity between the position of the motor and the position of the driven link. What happens if you don't model this joint elasticity, and if this joint elasticity is non-negligible? Of course, you can do this because you don't know in advance, and in fact, you have to put limitation on your performance, so you cannot go too fast, you cannot carry too heavy loads, and you cannot switch from contact to free motion without incurring in some shattering and vibration. Okay? And here I have a couple of examples. This is an industrial robot, a KUKA, with a heavy payload. And this is on-irregular, so without the new controller. This is work done a few years ago. And here you see a perturbation, although the robot is very stiff, very heavy, but the joints are compliant, especially when you're carrying heavy load. And you have this kind of low damped vibration. These are only due to the joint elasticity. And here, again, is a comparison between the original controller and the one developed by the PhD student here. So standard regular. So this end effector is doing a path like a square in the three horizontal, vertical, and normal plane. And here you can see the comparison between a controller which takes into account in its design the presence of joint elasticity and one that does not. The new regulator is the one which, of course. Okay, I think, did it run? Yes. Okay, so sources of joint elasticity, for instance, the whole series of DLR arm, because of the fact that the motor should be light and this robot were supposed to go in space and move relatively lightweight links, but still in a very constrained environment. So they used harmonic drives as a principal design, plus multiple things. This is the DLR Series 3, the last one that DLR produced. Then you know that this project developed into an industrial product with KUKA, LBR4, and then now the IVA manipulator. So here you have a typical explosion of an harmonic drive with a wave generator, which, well, I'm not going to go into the detail of this. It's too long. I mean, and you probably know how this works. But as you can see, there are two variables that we have to introduce. One is the motor position, which is attached in this configuration to the wave generator, while the circular spline is the one that drives the load. So you have a theta variable and a q variable, which are dynamically related, even beyond the fact that there is a reduction, a constant reduction ratio. They are dynamically related because of the flexibility. Here is another example. This is an arm developed in Pisa, but by another company, not our friends here from Scienza Macchinale, many years ago, used by Paolo Dario in some of his project, and we had a copy of this robot for a while in our department. It's an 8 degrees of freedom modular structure. Most of the actuators are concentrated. So there's one actuator here and one actuator there, so 2 motors, and then all the remaining 6 motors for the 8 degrees of freedom are placed in this link, and then they go through the structure through pulleys and cables, and of course these steel cables are very flexible. If you stack the motor, if you break all the motors, and especially in a straight configuration, and you push on the end effector, of course this is very compliant. Okay, so this is another thing that you can, of course you have to model and identify the stiffness parameter, but then you can use it as if you had a concentrated spring at each joint. There is also some coupling here, but of course this can be taken into account. This arrangement makes sure that it enables the fact that this arm, which is a human size-like, as you can see, probably, is 20 kilograms as a total, okay, in motion. And then this is our known. I took one picture from, I don't know if this is running, probably not, okay, it's not important. This is one of the first prototype in 2003 by the University of Pisa. And again, here you can see the situation. Well, this was a video. Actually, this is the actual prototype. You see the 2 motors and 1 output shaft with the link. And so you have this arrangement that provides a nonlinear flexible transmission between the 2 motors and the single output load. So in this sense, this is a generalization. You have to model these things. In particular, this works if you want to use the 2 motors for changing the stiffness, provided that you have a nonlinear stiffness characteristic. Okay? While for the joint elastic case, we typically remain in the domain of linearity, although you can consider also some nonlinear effect, but you excite this nonlinear effect only through motion, and you cannot control directly the actual deformation. Okay, so we focus now on this situation. This is just a single joint. Theta is the position of the motor, Q is the position of the driven link, and you have some elastic torque going through the transmission. The transmission has some stiffness K, and let's say constant stiffness. And then you can model the dynamics of this system just by using, for instance, the Lagrangian approach. It's the most convenient one, probably. So you build energy, kinetic energy, potential energy. You include in the potential energy also the one due to the flexibility of the transmission. And then you set up a set of generalized coordinates, in this case, 2n generalized coordinate, if n is the number of joints, so 1 coordinate for each of the motor and of the driven link. and then you apply Euler Lagrange equation. So if you do this, you have to derive all these energy terms. So there are some basic assumptions which are really always satisfied, at least the first two. The third one, most of the time, let's say 95% of the time. The last one, it's an approximation, but it's very reasonable when you have a large reduction ratio. So the first one says that, well, simply, we are in the linear elasticity domain. This is an assumption. You can relax this without major problem, okay? The second is obvious. So all the motors are balanced, so which means that the center of mass of the rotating motor, we are assuming electrical motor, let's say DC motor or whatever, is on the rotation axis. Otherwise, you would throw this motor away after a few minutes, few hours of operation. Okay. The other assumption is more at the system level. So each motor, let's say, suppose that we have one motor for each joint. But anyway, even if we have combination in parallel, so each motor is mounted along the open kinematic chain in a position which precedes the driven joint. Okay. You typically think of a motor mounted like this exactly on the axis of the joint, but this is not really the normal case. This is included in this assumption. So either is here or is before. There are situations, for instance, joint 3 of the joint 1, 2 of the Puma arm has the motor mounted on link 3. Okay. Like a horse driver, no? Mounting on this and rotating like this. But this is quite an exception. So this is a kind of a reasonable assumption which is used later on. And with this assumption, so you can skip things. These are standard notation, but just to focus. So this is the total total kinetic energy of the links, so the sum of all the links, which has a linear part and an angular part, and can be written like Koenig theorem like this. And once you work out everything together with some recursive methods, whatever, you end up with this structure. Pay attention, there's an L here characterizing the fact that this is only pertaining to the links, not to the motors. Okay? Then you have the motor kinetic energy, and in particular the linear one, so just associated to the linear velocity of the center of mass of the motors. And in fact, you have only this component. And again, this ends up with some matrix M subscript small m. When you sum up all this part, you end up with the M of Q that we are going to use. Okay, so pay attention. This means that it includes also the kinetic energy, the linear part of the kinetic energy of the motor. What about potential energy? Of course, you have the gravity part, which is pertaining to the center of mass of the link, and the gravity part, which pertains to the motors. Okay? And now, this is already something which is worth pointing out in the previous slide and in this slide. The assumption of the balance of the center of masses of the motors on the rotation axis implies that you have independence from the motor position in this expression, in particular on the gravity term and in the inertia matrix pertaining to the link and to the linear part of the kinetic energy of the motors. And then you have the additional potential energy due to joint elasticity. Here, assumption A1 works because we are assuming linear domain, so quadratic potential function with a constant k, multiplying the deformation, q minus theta, so k is typically diagonal, and it's positive definite. Okay, so you have all the potential energy you need. What is missing still is the angular kinetic energy of the motor. And here, the famous, at least for me, assumption introduced by Spong in '87 while I was doing my PhD. At the same time, we were working on this modeling and control, says, well, rewritten in my terminology, says just that the angular kinetic energy of each motor is only due to its own spinning. So if you have an arm moving like this, and of course you have motor mounted on that, even if one motor here at my elbow is not moving at all, it will contribute to the angular kinetic energy because it's an inertia body which has its own angular velocity imposed by the previous joints. Okay, so this is neglected by this assumption. Only if the motor is moving and with its own spinning velocity, this is the contribution to the angular part of the kinetic energy. I hope this is clear enough. And this is very reasonable, especially if you have large reduction ratio. It's not perfect, but it works. And in practice, this has become the standard. So once you have put also this assumption 4 and you build up the Lagrangian with the total kinetic energy minus total potential energy, and then you have this 2n-dimensional set of generalized coordinates. You apply the Euler-Lagrange once for all. You will never use this again because you already know what is the output, what is coming out. For instance, you never reintroduce this and then make this derivative because you already know that in the kinetic energy, what is here and here is actually in the quadratic form, so you don't need to do partial derivative if you're deriving these models in a symbolic way. So the end point is this one, and we will start from this two set of equation, which I call link equation and motor equation. This is up to here is exactly like the rigid case. In M, you include already the presence of the motors, okay? At least of the linear part of the kinetic energy. These are the Coriolis and centrifugal terms. This factorization is such that m dot minus 2c is Q-symmetric if you wish, otherwise you don't need that. And here, of course, you don't have any non-conservative force performing motion on the link coordinates. We are assuming that there's no dissipation term and no external force acting on the link, while the torque produced by the motors produce works on the motion of the motor variable theta. B is the inertia matrix. It's diagonal of the motors. And then you have the stiffness term times the deformation. Of course, this is equal and opposite here. Sometimes you see this term going to the other side. And then you can interpret the link equation like a rigid body, rigid robot model, not driven by the torque produced by the motors, but driven by the joint elastic torque. Okay? So you have kind of a cascade situation, and this is used also for control. So these are the some comments. The first one I already mentioned it. The second is very interesting. So what happens if k goes to infinity? You should recover the rigid robot model. In fact, you do, because theta tends to be equal to q. Remember that theta is now already after the reduction ratio, so the dynamics of these two variables is pretty much aligned, and if k goes to infinity, they are really moving in the same way. So you have k going to infinity and this going to 0. The product is non-definite, but in fact is converging to a finite value because it's just the transmitted torque produced by the motor going to the links. Okay, so what can you do? Instead of looking for this limit process, you can go back and you just add up these two equations, okay, so that this term cancels, so you don't worry about what's the fate of this infinite times 0 form. And of course, but you keep q going equal to theta, so this theta double dot becomes q double dot, and so you have this b adding to this part, and you end up with the equivalent rigid model, which, pay attention, is exactly what you expect, with the diagonal B matrix adding to the residual part of the kinetic energy that we have computed so far. When you have joint elasticity, you have to split these two parts. And if you remove the Spong hypothesis, then this splitting is not so clean as here, because you have also coupling terms appearing. Then this is another famous inequality, just because the gravity part is acting only on the link side, because the motors are balanced with respect to their center of mass. So you have that the gradient of the gravity vector, so the Hessian of the potential energy associated to the gravity, in norm is upper bounded by some constant alpha. Okay, and which implies also this inequality, which is very convenient in proving global asymptotic convergence of PD plus controller. So I would invite you, when you have time, to apply this, for instance, to this simple structure, and to understand what is the role of the single assumption. So here it's a planar 2R robot with elastic joints. This could move in the vertical plane, so you include gravity, or in the horizontal plane, so you don't care about that. And of course, you have a position of the motor here. Then you have a reduction ratio N1, so theta M1 becomes theta 1, and then you have the elasticity with the stiffness K1, and then you have the position Q1. The rest are obvious notation. And in particular, you will see that when you compute the kinetic energy of this second motor, now the two motors are placed exactly at the joints, then you will neglect something if you take the assumption of Spong. Okay? And you will see. Otherwise, you will have some coupling in the total inertia matrix. It's not partitioned with M and B in block diagonal. You will have some off-diagonal term, and this creates a lot of problem from the control point of view, but I'm not going to talk about that. So with this model, what you can do? You can do inverse dynamics. So what is you're interested in the position of the link, not of the motor. So you may assign, as if the robot was rigid, some Cartesian motion to the end effector, do some inverse kinematic, and have some desired trajectory for the links. So some QD of t. And inverse dynamics means if I want to have some motion of my links, what is the input torque that I need to apply? For doing this, I need to compute the trajectory of the motor, which is not given a priori and depends on the dynamics of the system. Okay, but this is very simple because you just take the link equation, the first set, where theta appears in a linear way. If the joint is not fully elastic, so you have some nonlinear effect, then this creates some problem because you probably need to solve numerically this equation, but this is kind of simple. In this case, you have an explicit closed form expression for theta, okay? And this is, you've set all the other terms depend only on q, so you set the q desired there. And then you can take the derivative of this, and in fact, you have the motor velocity associated to the desired link trajectory, and you see that here some very complex terms appear, but they can be computed. For instance, you take the derivative of this, and this provides this term and these terms because you take the derivative of the inertia matrix with respect to time, and so on and so on. And this is the notation that I'm using here. And now you have to do this one more time. So you take the second time derivative, and you have the acceleration of the motor, desired, associated to the desired acceleration of the link, plus, again, terms that now we understand how they are. For instance, this g double dot is the second time derivative of the gravity vector. It's a function of qd. Originally, once you take the two derivatives, this is internally a function of qd, q dot desired, and q double dot desired. Okay? But everything is desired, so everything is known in advance, so this can be computed. And now the last step is very easy. You just take this expression, instant by instant, and you plug it into the motor equation, and you have the desired torque, which takes this nice form. So you can reorganize also things. And in particular, you can see that if you let k now go to infinity, so all this extra term, these long terms, just vanish, and you're left with the conventional inverse dynamic of a rigid robot. Okay, so mq desired plus b, the inertia, the diagonal inertia matrix of the motors, and then the Coriolis terms and the centrifugal terms and gravity terms. Okay? Now, all this suggests that if you do this for a 2R planar robot with elastic joints, it's fine. If you do this for a 7 degrees of freedom robot arm, you start running into trouble. If you do this for a 45 humanoid with compliant joints, well, you may take a long while to get into the Lagrangian expression, and then you have to evaluate this for the inverse dynamic, not in real time, but still later on for feedback control, you need to evaluate these terms in real time. So this is quite complex. So this is why one can develop. Actually, this is work that has been around for a while, and now we're producing a paper on that. So a modified Newton-Euler method, so that you have to know all the dynamic parameter, but then you can compute recursive expression, so in a linear complexity time with the number of joints, so that you end up with computing this numerically and never building the symbolic model of your robot. So this is quite convenient. So when you move from offline computation, inverse dynamics, and pre-planning, and so on, to online, you need sensors. So what is the change here? Well, we have seen that we have two variables for each joint. So if we want to apply a full state feedback, we need to sense the four variables. So the position of the motor, the position of the link, and the velocity of both sides. Okay, so we have 4n state variable for this n degrees of freedom elastic joint robots. Typically, especially if you don't know if your robot has elastic transmission, you just mount sensor on the motor side. So you measure theta and theta dot. Theta dot, in the old days you had tachometers, now you just have very accurate encoders, and so you take all the velocity by numerical differentiation. Okay. Of course, if you know instead that you have this issue, then you mount additional sensor, either position measurement beyond the elasticity, or some jointor sensor, which can be used in combination with the motor sensing to provide information on the link side. Okay? And you have different combination of that. For instance, this is an exploded view of the famous DLR-3, where you can see that this has all been designed and optimized in space and in weight. And here, about sensors, you have, where is it? The first position sensor on the motor, so before the transmission. Then you have the harmonic drive. And then you have also a link position sensor. And then you have also mounted a torque sensor, which measures the transmitted torque. So in fact, you have 3 sensors for 2 variables, so you have slight redundancy. Then in practice, at DLR, they're using only the motor position and the joint torque sensor. And from there, knowing the stiffness of the transmission, they reconstruct the position of the Q. And this is also my interpretation of what KUKA is doing with this fast research interface. Okay? So the user is provided with a Q variable, although internally the Q variable is not directly measured. So what are the basic control problems? Regulation, which means that we want to go to a constant equilibrium configuration. And the only thing that the task assigned is the position of the links, not of the motors. And of course, again, this position may come from some Cartesian specification. Or we want to track in a reliable way, which means not just starting on track, but even if we have some initial error or some disturbance that brings us away from the desired trajectory, we want to recover trajectory as fast as possible and as smooth as possible. You may suspect that since we are considering flexible system, the trajectory that we are able to reproduce exactly should have some smoother characteristic than those that can be reproduced by a rigid system. This is correct, and in fact the inverse dynamics just told us that we need to have the 4th derivative present in order to be sure that we can exactly reproduce a trajectory when we start matched with that. Okay, so again, so we are assuming that we have sufficiently smoothness for the reference trajectory. And then there are many other problems that we are not going to talk about. For instance, interesting here are rest-to-rest maneuver in given time, because you have flexibility and you want to eliminate this flexibility at the target final time. Or Cartesian control, like in rigid case, and or even force and impedance control. And I will say something about impedance because I promised to say that in my original title. And it's not a positive statement, but you will see later on. So let's start with regulation, and let's start with the most simple case. In fact, this is, I'm taking for illustration a device which answers cells for academic purposes. So it's a linear flexible joint, as I saw, so two masses connected by a spring moving in the linear plane, on a linear rail. And you can imagine that this is the inertia of the motor. In fact, this is the actuated part. So this is the position theta, and now it's a linear position, but you don't care here. Then you have some stiffness connection here, and then you have the unactuated link mass m, and its position is q. So if we neglect friction, in this case the model is very simple. It's linear, because there are no gravity effect and no Coriolis term. There's only constant term in the inertia and so on. So for instance, for this analysis, you can do Laplace transform and define transfer function from the input to the variable of interest, the position of the motor itself and the position of the link. Of course, you want to control this, but it's good to know to have also transfer function to the position of the motor, because you may need to close the feedback loop from that quantity, and you don't have an explicit measurement of Q, for instance. Okay? And I mention this as collocated transfer function if I'm taking this as output, or the velocity as output of the motor, and non-collocated in this other case. Pay attention, if you had distributed flexibility on the link, the non-collocated case is a case that is prone to have instability when you try to invert the reference trajectory for the tip of a flexible link, for instance. This is not the case here, but still the non-collocated means something. So the motor transfer function looks like this. So you have the rigid body motion, and then you have a pair of zeros and of poles. So the system is unstable because of this relation, but it's passive because if you look at these imaginary zeros and poles, you have a way of zeros always preceding the associated pairs. Here you have only one pair of imaginary zeros and one pair of imaginary poles. So this is a characteristic that can be interpreted as a passivity in this linear transfer function domain. Okay? So not in time, not in energy, and so on, but it's exactly the same concept. If you're taking the other transfer function, so from the torque to the position of the Q, still the rigid body motion, but you see that the zero has disappeared completely. Okay? This is the case of no damping, no friction, and no other effect. So in this case, there are no zeros at all. Okay, if you introduce some damping, then these pairs are moved to the left-hand side plane. So this is the limit case, and this is why you would like to consider also this limit case as the control design basis. Now, if you collect, have you ever collected some experimental frequency response? This is how the Bode diagram looks like. With anti-resonance and resonance, if you're taking as output the position, the velocity in this case, I removed the one pole in the origin of the motor, while you have a pure resonance in the case when you're taking the velocity of the link as output. Now, these are with no zeros or very practically no damping. If you add some damping, the profile looks pretty much the same, only they are more smoother. There is no variation of 180 degree, very sharp in the face, and even here everything is smoothed, but you can still recognize some peak in the frequency response and this anti-resonance resonance profile when the output is on the motor side. So this is something that I took from the chapter on the Springer handbook. So you can imagine to close feedback with partial measurement, not with the full state. So like a poor man design, you have only one position sensor, and probably you can extrapolate the second one with numerical derivative, let's say on one side or the other side of your transmission. So what happened? If you're doing pure link side PD feedback, so you're taking the position, the actual position of the link, so beyond the elasticity and of its velocity, and you build up the closed loop transfer function, and in particular using these gains, which appear to be here, you recognize that there are some terms power missing in the denominator, so this is always unstable. So you cannot do this, okay? While if you close the feedback loop all on the motor side, because of the passivity, but also because of this simple analysis, you see that this is asymptotically stable as long as you have positive gains here, no matter which value, like in a rigid system. Okay, this is very convenient. Of course, this is a fourth-order polynomial, so you have to apply the route criterion. Which is the fact that the coefficients are all positive is necessary, but not sufficient for asymptotic stability in the closed loop. So the other two combinations are mixed ones, so position of the link and motor velocity, or vice versa. Now this turns out to be always unstable. This has some interval of stability, but limiting the proportional gain, which is not really convenient. Okay, so this simple analysis shows that after all, if you want to regulate things, you have, and you don't have a full state feedback, you should close your PD controller on the motor side. This is the most convenient situation, okay? And in fact, if you do this and you don't have gravity, you have a multi-degrees of freedom elastic joint robot, this is perfect. Of course, transient may depend on several other choices, but asymptotically you have convergence, okay? So this means that we focus now on the motor PD feedback while moving from this single degrees of freedom case, linear case, to the multi-degrees of freedom nonlinear case. The other comment that I would make here is that, of course, if you have full state feedback, so measurement for all the states, all four dynamics, then you can impose, since the system is controllable, you can impose whatever dynamics you wish. But this dynamic should be of the fourth order. And we will come back on this when we talk about impedance control. So this is just, I mean, in case you're, if I see it, okay. So this is just a video by Quanzer that shows what is the behavior, and depending on how you close the, so this is the output mass, and there's a connection here that you can see it or not see it. This is the motor. This is the driving motor. So you see that is doing some oscillation, which is amplified. So it's near to the resonance frequency in this case, okay? So the motion of the motor is amplified at the level of the link, okay? And of course, here you have a rest-to-rest maneuver, and this is without output feedback, so this is just the intrinsic damping that lets stop the load. And here you're doing full state feedback, as I was saying. So you see that there is some residual oscillation, but it's pretty much a good transient behavior. Okay. So, without proving any results, now I will detail the basics of regulation for the general case, so in presence of gravity. So, the oldest results is from my colleague and friend Patrizio Tomei in '91. So, he proposed this kind of control. So, it's a PD control on the motor side. QD is constant, so theta desired associated is constant. So we are closing a proportional terms and damping out velocity of the motor and adding a constant gravity compensation term at the target destination, okay? From the beginning, if we want to be there and we start from here, right from the beginning we are applying the torque, the gravity torque needed to stay here, okay? So this is a linear plus constant feed-forward controller, so the simplest thing that you can think of. The only trick is that, of course, you have to provide this reference, and since QD is constant, in the inverse dynamic, everything blows out, and what is left is this part. So you see that the position of the motor should be different from the position of the link because of the load of the gravity. And this is less and less sensitive the more the joint is stiffened. Okay? So in case gravity is not there, of course, these two at steady state are exactly the same. Otherwise, you have a difference. And this has implication also for the variable stiffness case, of course. So what Patrizio showed at that time is that if you have a lower bound on some matrix, which is a combination of the stiffness K of the joint and of the proportional gain Kp, and if the minimum eigenvalue of this symmetric matrix is larger than alpha, the bounds on the norm of the gradient of the gravity term, then the closed-loop equilibrium state, that is that one with zero velocity, is globally asymptotically stable. Okay, this is a very nice result, I would say, and stayed for a long time there. And you can see that it moves from the rigid case to the elastic case in the minimal way. The only thing is that here there's a constant compensation. Even in the rigid case, you can compensate gravity only at steady state from the beginning, and in fact, you have a lower bound on Kp. Here, the lower bound is connected also to the structural stiffness. So if your joint is very soft, so K is going to 0, you may not be able to satisfy this. In particular, if the minimum eigenvalue of K is smaller than alpha, no matter how large you make Kp, you're not able to reach this condition. And in fact, this is what summarized in this simple case. So if, on the other, this is written in the other way round. So if the minimum joint stiffness is already larger than alpha, then you can satisfy this by increasing the minimum eigenvalue or the minimum diagonal element of Kp if you're using a diagonal Kp. Okay, and for doing this analysis, because of this matrix, everything is diagonal, so it's 2n by 2n, but in fact it's block of 2 by 2 matrices, and you can analyze the eigenvalue of the 2 by 2 matrix, and this is the expression. And then you suppose that you are small, largely, an epsilon larger than your K is an epsilon larger than alpha, okay? So you can see that you have a lower bound for Kp, which is 2 alpha, alpha squared over epsilon. Of course, when epsilon goes to 0, so you're not strictly larger than alpha with your structural stiffness, then you need to have a larger, an infinitely large Kp. Otherwise, this is a proof. Now, many years later, I restarted working on elastic joint control, and with Bruno and Loredana Zollo, we came out with this modification, trying to say, why cannot we do, like in the rigid case, that we have a PD and we cancel gravity everywhere, okay? This gives a lot of theoretical problem in proving things, so we end up with this modification. So we have a theta which is varying, in fact, is the position, the current position of the motor, which is biased by a constant term, which is computed only at the steady state. Okay? Now, I'm not going into the trick of this, but you can discuss this control law by saying that we were trying to cancel more gravity on line as possible. Okay? But again, using only measurement from the motor side. You see there's no Q ever here. Okay? So, unfortunately, the proof, we were not able to relax the lower bounds on K and Kp. So, what's the use of that? Well, these are sufficient conditions. So I just show here some simulation that we did at that time. And you can see it's a 2R robot in the vertical plane. The alpha is 133 here. So you should be at least twice as large. You should be... well, you cannot see it from here, but this set of gains satisfy the condition, and this set of gain does not. So you violate the sufficiency condition. Now, if you're applying Tomei's controller, in this case, you see that the error is not going to 0, while with our case, it's going to 0 and even faster. In this case, both go to 0, but this is much slower than canceling gravity as much as possible of the gravity online. Okay, so it is some practical value, it has it. And in fact, even at DLR, Christian Ott, Albus Schäfer in particular, 1 year later or 3 years later, they came up with a variant of this. No? Instead of having theta tilde, they have a Q bar. It seems like the same thing, but this Q bar is computed in a different way. If you look at the steady state equation, when everything is in equilibrium, whatever this equilibrium is, you have a situation like this. Okay, suppose that theta and Q bar are the equilibrium condition. Now, if I give you a Q bar, you can compute immediately the theta. But if I give, because I measure the theta, I need to solve this nonlinear equation and find the associated Q bar. Okay, and this is what they're doing with a contraction mapping. They prove that this, provided that K is larger than alpha, and in particular the minimum stiffness of the joint is larger than alpha, this converges in few iterations. Okay, so you initialize this iteration with one measurement of theta, and then you do 2-3 steps, and you have something that you can baptize Q bar, and you use this Q bar to compute the G. Remember that the G is a function of Q, but you don't have a measure of Q. So this is another way, it's a more sophisticated way than ours to compute these things. And in fact, they were able to relax the condition. So provided that this holds, then you have no lower bound other than having a positive gain for the proportional term. So after a while with Fabrizio, we found, well, this is still linear but requires some iteration computation. This is a nonlinear PD law with some what we call dynamic gravity cancellation. And we were able to prove global asymptotic stability for any K, positive K, and any positive Kp. So relaxing, I mean, this is the minimum requirement that you may think of. And that's it for regulation. What about trajectory tracking? As I said, the desired trajectory should be smooth enough, so there should exist the fourth derivative in much the same way as if you want to guarantee perfect tracking in the rigid case, there should be an acceleration. Even if it's discontinuous, then you will have discontinuous torque. But this is the minimum requirement. Here, the fourth derivative should exist. We are assuming the full robot state is measurable, and again, we have a good dynamic model of our robot, including stiffness, possibly after identification. So these are very strong assumptions, I would say. With this, it's a joke to design a controller, okay? But at least if you do that, you should do the design in the right way, and many people haven't done this because they said, well, in order to do feedback linearization for this class of robots, you need to measure jerk or whatever, and you never will have this, okay? But if these are the conditions, then you just need to measure whatever state you have, okay? So nothing more than what you expect, okay? In fact, if you design following there are books in nonlinear control, you have to put the system into the state space form, and this is what Mark Spong did at that time. But in fact, you can reformulate things directly on the second-order dynamic model of your robot without referring to Lie brackets and involutivity of distribution and things like that. So things are much more easy to understand. Okay, so the assumptions are strong, but the result is very strong. It's the best possible result that you can imagine. So you can stabilize the error around a smooth trajectory at an exponential rate, not asymptotic, and you can impose this rate by choosing your gains. So more than this, of course, it's impossible. So this version is the generalized version of the computed torque law for the rigid case, I would say. Okay. So let's see how it works. It's 2 slides, and if you understand the concept, it's very easy. So you take from this equation. This is the link equation. Now I just wrote this in a more compact way just because I don't want to carry over too much terms. But of course, if this is a 7 degrees of freedom robot, there are a lot of elements inside that part. Okay? So here there is no, you want to build this system inversion. So you want to assign a trajectory for Q. So Q is your output. You want to invert the system and find the input, the torque that reproduces, like in the inverse dynamic case, but now using the measurement in real time from your system, okay, using feedback. So here you see that there is the second derivative of your output, but there is no input tau. So you just take the derivative of the whole equation. And this, again, brings you to mass times jerk, m dot times acceleration, time derivative of these terms, and then again here. Still, you don't have dependency on tau, so you have to differentiate one more, so that by doing computation here, you have, pay attention, always the original inertia matrix, so this is guaranteed to be invertible, multiplying Q 4 dots, and then here you have theta double dot appearing, and then you rely on the motor equation because this theta dot is the same as here, so you can use this equation to let tau appear and then cancel whatever nonlinearity is there so that to isolate Q4 dots. Okay, in fact, when you substitute things and you build up this very complex term, okay, and then you cancel all nonlinearity, like you do automatically in the rigid case, but now you do it at a higher differential order. So this is the control law, and this is the result. Not surprisingly, it's not a double integrator, it's a fourth order integrator. So you have n chains of independent 4 integrators from each new input A to each position Q for joint by joint. So you have linearization and decoupling. So, and now the comment. Can you compute this control law, which apparently depends on theta, on Q dot, on Q double dot, and Q triple dot? Okay, so this, here, at this point, many people stop and say, no, this is bullshit. Well, if you have a model, then, and this is something that you never have to do in the rigid case. So you need to invert the inertia matrix, or to use articulated body method to avoid the build-up of the inertia matrix, the isolation of the acceleration. Okay. So in any case, from the link equation, which is not dependent on tau, you can always isolate the acceleration, and this is its expression. So Q double dot is a function of Q theta and Q dot, which is what you're supposed to measure. Okay? Now you save this, and then you move to the first derivation of the model, of the link model, and then here again, the M was the leading term to the jerk, so you can isolate the jerk. So Q triple dot is a function of Q theta dot, Q dot, Q and Q dot, Q double dot, but Q double dot is already a function of this, and you save this information, and so on and so on. Okay? So you can see that you don't need to measure Q double dot and Q triple dot, provided that you have a good model. Of course, there's an issue of robustness, okay, but this is a different story. So, in fact, the full law, if you do this numerical substitution, you don't need to substitute analytically this term, just evaluate terms and plug them in. So this is a nonlinear static, so instantaneous feedback from the original state. And this is really feedback linearization. Now, we have this chain of 4 integrator. We have to stabilize around the trajectory errors. This is done in a generalized way. So it's a PDDD controller with the feed forward of the desired fourth derivative. Okay, so this gain should be positive and diagonal, but this is not sufficient because it's not a second order system, it's a fourth order system. So you have to guarantee that the diagonal element of these gains, which build up for the generic joint this fourth order polynomial, the root of this polynomial should be on the right, on the left-hand side of the complex plane. So this should be a Hurwitz polynomial. And this guarantees asymptotic stability, but in fact exponential stability because the system has been converted into a linear system. So asymptotic is equal to exponential in this case. Okay? So this is a very powerful result under strong assumption, but this is what I wanted to mention. Now, it's interesting to see that this design that we have, why were we able to, we have not checked necessary and sufficient conditions for feedback linearizability. We just built the controller, constructively. So we solved the problem in a constructive way. But the reason why this works is related to the same observation we made in the single input, single output system of a linear transfer function. So in terminology of nonlinear control, the system has no zero dynamics, which means in the linear transfer function that the output that we are controlling, the transfer function from the input to that output has no zeros. Okay? And this is the nonlinear time-dependent concept in the time domain. Maybe some of you have heard about flat outputs, and this is exactly the same. So I would say, since the system is feedback linearizable, then Q is a flat output. So it's, in terms of nonlinear control theory, the Q are linearizing coordinate. Somebody has called them also flat output. It's exactly the same thing. Now, of course, there are some simplification of that. Of course, you can simplify things. Okay, I will skip this. You can have, of course, you will have copies of these slides at the end of the course or tonight. So, very few people have implemented this type of feedback linearization controller. What they have implemented is this kind of local asymptotic stable controller. So they have computed from the Q desired, they have computed the theta desired and the theta dot desired, so the trajectory of the motor, plus the feed forward through the inverse dynamic, and then they have applied the PD on the motor side, but on time varying now motor reference, plus the feed forward for the torque. Okay, and this works pretty much reasonably. Of course, it has no linearization or decoupling properties. So if one joint is going out of its trajectory, in order to recover that error, also the other joints are involved. The decoupling instead, when you have all joints starting in the right way and only one joint which is off its trajectory, the decoupling controller will compensate for that and recover that error without disturbing the other joint motion. This is the nice property of decoupling. So a note on impedance control. This is the time. So feedback linearization is, I would say, an exceptional design tool for free motion control. Up to now, we have not seen any interaction with the environment. What about tasks that would imply, at some stage, some interaction and some need to control the exchanged forces? So if we have rigid robots, we can do this in several ways. But in fact, the impedance controller is nothing else than a feedback linearizing controller, so converting the system into chains of double integrator, and then selecting the acceleration A on input of this, so to match a desired mass spring damper model, linear or non-linear, typically linear and decoupled. Okay? So, and in particular, if you assign arbitrary target value to the spring and damper, so the stiffness and the damping, then it's what you call actually compliance control. If you're also modifying the mass, then you have a target inertia, replacing the actual inertia of the robot with in the joint space or in the Cartesian space, or at the contact point where you have the interaction. Then this is really impedance control. And in that case, as soon as you modify the inertia, you need to have a measure of the contact force. Okay? So if you want to do impedance control in the joint elastic case, you may think, okay, I apply first feedback linearization and I obtain this decoupled system. Can I achieve at this point the same performance as in impedance control? The answer is no. Okay? Or not in a clean way, not in that easy way as you can do once you have all set up in the rigid case. And in fact, what are the problems? First problem, if there's a contact force on the right-hand side of the link dynamics, remember, we have differentiated the link dynamics twice. So if a contact force is there measured, we need to differentiate this twice because we don't have a direct measure of the derivative of the contact force and of the second derivative of the contact force. Here I cannot go out of this point. So this is one basic issue. But suppose that you get around this problem in some approximate or estimated way. Then you have a second problem, which, to my knowledge, nobody attacked right now. So you have a fourth order system. So what kind of fourth order target impedance are you going to choose? What is the good model for a fourth order mechanical system? Okay, you take a mass, spring mass with a big mass and a very tiny mass so that this is almost equivalent to having just one mass, or you try to distribute the masses between the total mass between these two elementary masses. So this is an open issue. It's a matter of targeting your desired behavior with an impedance scheme. So what do people do in practice? So this is the no part. Now the not clean way. So people do things. And in fact, we've been doing also something. And what you do is a kind of a backstepping-like design. So you assume on the link dynamics that your elastic joint torques are really directly controllable, okay? Like input, like current that you can impose to your DC motor. And so you have exactly the rigid case. So you design whatever controller, including impedance controller, including the fact that you measure the force there, and you have an expression for that. And then you try to design a control law that try to impose this elastic joint torque with your motor torque. So you do a step back, and you move from the second order dynamic of the link side to the full fourth order dynamics when your input are the motors, okay? And this is in practice what also KUKA is selling with his robots. When they said our robots are torque controlled, so you can impose your own torque. This is not really true. What they can do is exactly have a very tough and well-designed second step controller so that whatever torque you want to impose to the link dynamics, doing local feedback, he's able to impose. So you specify as an end user some torques beyond the elasticity, and he uses joint torque sensing and whatever design of the local loop to do this in the best possible way. Okay, so that it's completely transparent to the end user. I mean, if we were not an academic professor, probably few people around the world worry about this. You just use this robot as if they were rigid. Okay, in fact, you don't have even information about the actual stiffness and other parameter, the local controller inside this. Okay, a few extension, very. How much time do I have, Giorgio? It's okay. We have still time. VSA-based robots. So here, as we said, we are interested in seeing if these techniques, Lyapunov-based or based on feedback linearization, can be used also for variable stiffness actuation. Okay. So in particular, we want to check directly the difficult case. So if those systems are feedback linearizable, and in particular, also input-output decouplable. Pay attention, since here you want to control two things for each joint, the motion of a joint and the stiffness of the joint. So even if you have only 1 degree of freedom in the conventional sense device, so you have 2 inputs and 2 outputs. So the problem of decoupling makes sense. In the joint elastic case, decoupling makes no sense because you have 1 input, the torque, and you want to control the motion of the link through the elastic joints, but you cannot control the joint stiffness, okay? So decoupling is important. It's coming for free in general, but in this case it's very important even if you have only 1 joint, okay? And then you want to track some smooth reference trajectory. How smooth you don't know in advance, okay? And these trajectories are probably according to the Brachistochrone studies of some optimality. So, for instance, for safety, you want to be stiff when you're moving slow and then be soft when you're moving fast, according to some limitation. Okay. So this technique is good because it applies to 1 degree of freedom, but under suitable assumption, it's straightforward also for the multi-degrees of freedom case. So I will show it on some specific example, the SVS-A2, which is a variable stiffness device of the antagonist type. Okay, and then, but the same applies also. We have applied also to other serial type of variable stiffness actuators. So, more or less, this is the situation. There are 2 motors. This is the device open. The spring, the transmission are non-linear, but they are using pairs of linear spring, but they have a 4-bar link. They had at that time, though, I don't know if this developed later, a 4-bar linkage that introduced the non-linearity which is needed to change the total stiffness of the actuators. And this is the Grashof pair, and you see that we are commanding this phi, this or giving a torque here, or directly, if we assume that this is reasonably fast, commanding phi desired or phi dot desired. When we're moving this, we are compressing in a nonlinear way, which depends on this kinematics, this linear spring, and this changes the points in the characteristic curve, which is nonlinear. Okay? And then you have to work out some geometry, and here you see that you have a function between this angle, how you compress the spring, and this angle. So it's actually a reverse function from beta to phi. Okay? But it's invertible. So, in fact, you invert this, so you command phi and you modify b, and with the b you load the spring, so you have a potential energy, which is a quadratic function of the deformation, because this is a linear spring, so it has its own k. But in fact, since you're moving phi in a nonlinear way, so you're changing beta in a nonlinear way depending on what you control, this introduced the needed nonlinearity, and then from potential energy you compute the elastic torque or the flexibility torque associated to this by doing one gradient, one derivative, and then doing again a second derivative, you have the stiffness. By the way, whatever is the form of this part, so whatever is the function beta, these steps are exactly the same for all situations. So this is kind of convenient. And if you want to look in particular with the numbers that we had from PISA, this is the nonlinear deflection beta as a function of phi. This is the potential energy. This is the joint torque. You see that it's antisymmetric. This is always positive. And this is the positive stiffness with a minimum positive stiffness in this case. Okay? So this changes according to the device of the mechanical design and so on. But this is the situation for this VSA2. So the model is this was for one single device. So now this deformation, since we have a pair of devices, so the deformation will be the difference between the motor position 1 and the link position, and the motor position 2 and the same link position. And then you have a total joint torque, which is just the sum of the two multiplied by 2, because we have two linkages for each motor size. And the total, or so-called device stiffness, is just the derivative of this with respect to the variation of Q of the total joint torque, so it has this expression. Now, if you imagine to have a link moved by the VS2, but this link is moving in the vertical plane, so you have a load which you can model in this form due to gravity, and this is the total situation. So this is the dynamics of the motor. If you remember the joint elastic case, we had only one of this and then the link side. Now we have two of this with a nonlinear joint elastic part. Here it's not k times the deformation. This is nonlinear. And then, in this case, the sum of this is found on the other side, together with some external additional, let's say, collision torque that we don't consider from now on. So this has 3 coordinates, so 6 states, including the velocities. And we have 2 inputs, tau 1 and tau 2, and we want to control certainly the motion of the link, so Q, but also we want to control the stiffness. So we have the 2 outputs are here on the screen, the 2 input already, and the model. So we have set all things in order to apply the theory of control. In particular, we want to do this inversion algorithm like we did in the conventional sense. So we define the 2 outputs, Q and sigma, and now we differentiate the output as many times as needed until in the expression of the derivative of each derivative, there will be at least one input appearing, okay? And then we stop. When we do this for both output, we may need to differentiate a different number of times the 2 output until this happens. And then the matrix that multiplies the 2 inputs in this order of differentiation, which may be different for the 2 output, is the so-called decoupling matrix. If this is non-singular, we can invert and linearize and decouple the input-output behavior. If the number of times that we have made, the total number of times that we have differentiated the 2 output equals the number of the states, the dimension of the state space, then the same control law, rather than just doing input-output decoupling also exactly linearizes the system. So there is no unobservable part in the closed loop, which is still nonlinear. Okay? So let's check this, and in fact, this is what happened. If you take the position, you have to take the first, the second derivative, this is its expression, but still neither tau 1 nor tau 2 is appearing, so you take a further derivative, and then you use the expression of these parts, and then again, here, you're not yet at the desired level, then in the fourth derivative, you have some nonlinear function, and finally, you have both torques of the two motor appearing, tau 1 and tau 2. Okay, so you stop here. And so if you factor out tau 1 and tau 2, whatever is multiplying is the first row of the decoupling matrix. If you do the same for the stiffness output, so the stiffness per se is not a direct function of tau 1 and tau 2, so you take the derivative and you have this expression. Again, there are only velocity involved. Once you take the second derivative, now through the theta 1 double dot and theta 2 double dot, you will have tau 1 and tau 2 appearing, and you see that these are the coefficients, and this will, if you factor out tau 1 and tau 2, this will be the second row of this decoupling matrix. So the whole computation can be organized in this way. You see 4 times derivative in y1 and 2 times derivative y2, which is the stiffness, is a nonlinear function of the state plus a 2 by 2 matrix function of the state multiplying the input. So if this is non-singular, you can invert things. So you can cancel all nonlinearity, replace this, so that the fourth order derivative of the first output will be equal to the new signal V1. So it's a channel with 4 integrators at this state. And the second channel is a second order set, okay, of integrator. And the total is 6. 6 was the number of states at the beginning. So you have covered all possible dynamics of the system, so there's nothing else than a chain of 4 integrator and a chain of 2 integrator in this case. Okay? You see, it's very consistent as a method. Now let's look at the decoupling matrix. This 2 by 2 matrix has this expression, so the stiffness of the first transmission, of the second transmission, and the gradient of the two stiffness with respect to the respective motor position. Okay, you can factor out some gain, and now if you look there, this is only a function of the variation theta 1 minus q, so the deformation of the first transmission, and theta 2 of q. So you can do a plot in 3D, where here you have the two deformation of the two transmission, and here is the determinant, let's say, okay, and then you can play around with MATLAB so that you can see that the zero, this is exactly a side view of this leaf. And you see that the zero happens only when those are 0. So this is singular if and only if the two motor positions are exactly the same. Okay? Which means that you have to preload in a certain way this device, as long as this model is the correct one. Maybe there are some changes. But if everything is consistent, then this should be avoided from the beginning. And if you avoid it from the beginning, then you will guarantee that things will perform as desired because you're enforcing. Yeah? Sure.
Yes, in your equation, in the previous slide also, in the...
Previous?
No, okay. No, all of the slides, you modeled the dynamic of the motion and also the stiffness. But my question, how do you dynamic the displacement and vibration, and how do you prove that when you control, how do you prove that your controller
works
and the down vibration and displacement?
Well, in fact, you're right. In fact, in this method, I don't use a Lyapunov function. Why is that? Because when I have converted the system into a linear system, then for me, the proof is just assigning poles or eigenvalues, and this is done by those gains. I don't have to care about anything else. So, will I damp things? Well, it depends on where I locate my pole in the closed loop.
Sorry, but we can also control the care about the displacement or vibration?
No. Pay attention. The PD or PID that I'm applying is beyond the nonlinear feedback controller. It's not just that I'm saying, well, a PD or PDD, it's working. This will not work. I mean, it may work, but then I need to study if it's stable, if it's, what happens to the transient. So it's just the concept of feedback linearization. The concept of feedback linearization means that you have a nonlinear system. You have a nonlinear controller. If you put them together, the behavior of the system is up to uncertainty, is exactly that of a linear system. And now if you have a linear system and you can close, and it's a controllable linear system, so you can assign eigenvalues or poles, whatever technique you prefer to do LQ design or even H infinity design, but then you have guaranteed performance. So you don't need to resort to something which is still nonlinear and then you have to analyze the behavior of some variable which are not directly controlled or whatever. I don't know if we can discuss further this. It's a critical point. Of course, you're right. I never said prove that it works. Because when I reach the linear single input, single output controllable side, I said, I'm done. Okay? In a sense. Okay? So here you say, exactly. You could, for instance, you could take this as your controller, just this. You say, I'm looking at what is the desired stiffness. I'm estimating the stiffness if I'm not measuring somehow. In fact, I'm estimating that. And again, I have some profile, so I may have a sigma desired dot or zero. Maybe I just want to go to a constant level. And then, so I damped the variation that I estimate from my actual stiffness, and this is also zero. And then I use this multiplied by again as one of the inputs. By the way, since this is a completely symmetric system, the two motors are equal, then I don't even know which motor is doing this. Okay? In fact, the methodology is just will assign automatically part of this task of regulating the stiffness or of following that motion to both motors. Okay? In an automatic way. It's in the equation that we have written. Okay? So, again, so you have understood the story. Again, what should we guarantee in order to be able to reproduce this profile? Well, again, as in the joint elastic case, there should exist the fourth derivative of the link motion. And the desired profile of stiffness should be twice differentiable. Now, what if we decide to have a constant stiffness and then to change the stiffness as a stepwise, let's say go to the smallest one to the largest one instantaneously? Will this controller have problems? No, simply it will never realize immediately this value. It will grow to the desired new constant value that you have changed in a stepwise with an exponential transient. And the exponential is dominated by these two gains. Okay? So requiring sufficiently smooth is just if you want to do perfect reproduction of your profiles. Then you have profile that switches instantaneously, it's fine. You will, even if you are attached to your reference at that point, you will be detached because the system is not fast enough to follow this variation of the derivative, but you will be recover the new values with the transient specified by this part, the linear part and decoupled part of the controller. Okay. Well, this is very simple simulation. For instance, this is an initial match condition. So I'm taking smooth references like polynomial terms with zero boundary condition on velocity, acceleration, jerk, whatever, rest to rest or from this position to this position. And I'm guaranteed that I'm there, the system is at rest, so the initial state of the device is matched with the correct number of derivative of the reference profile, Same thing for this profile, and you see that I'm starting for 4,300, then reducing to 4,000, and then amplifying. This is really the kind of brachistochrone, safe brachistochrone optimal profile. And when I do things, you see this will be the torque applied to the two motors. Similar, but actually kind of complementary, if you look like, depending on what you're doing here. So automatically you're distributing these two tasks to the two motors thanks to the nonlinear feedback, which in fact couples things inside the device in order that the controlled output behave as decoupled. So it's like reverting a jacket in this sense. Now, everything was perfect, so there was no initial error, so you don't see any error here. If you start with some initial error, for instance, here I'm starting, the reference position is 0 and goes to 90 degrees, so 1.57 radians, and you start with 0.2 radians, so you have an initial error. And here I don't remember if I have very small stiffness error. So you see that you converge, and similarly here, but in fact the presence of an error here is not really affecting the behavior of the stiffness profile because of the decoupling property. And again, there is some perturbation here of the nominal torque if we had started matched, but the error recovers in an exponential way. Okay, so let's move to the next topic. Perfect cancellation of gravity in a flexible system. Okay? So what do I mean by that? We would like to mimic the same situation as in the rigid case. So the robot should behave as if the gravity was not there. No, we know that for the rigid case, we just cancel gravity and then the system is floating in the absence of any other input in space. It stays there. If I move it, it goes to another place, but it stays there, and so on and so on. We would like something similar for a flexible system. Is this possible at all? This is the first question that we have to ask ourselves. So we may relax this requirement, because in fact it's not possible, and say, well, let's say that some output variable, the one that I'm interested in, behave as if there were no gravity acting on the system. Okay? Because if this happens, then those variables, which are the one that qualifies the performance of my system, for instance, the fact that a flexible robot is reacting to a collision and going in the right direction without the effect of the gravity, so biasing the response with gravity, and this is really a practical aspect, then this is achieved. Okay? And so some output variable should match the behavior of, let's say, a model of the same system which is living in the far space where there is no gravity at all. Okay? Suppose that you have the same identical system but without gravity. So the same variable should behave in the same way, with gravity and without gravity. Of course, the input may, and in fact, react in a completely different way, but this is a different story. And this should happen not only in static condition, at steady state, but while moving at any time. So we are really asking quite a lot. And of course, we would like to have these things applied for the single degree of freedom case or for the multiple degrees of freedom case, and for the whole range of elastic joints or flexible joints with nonlinearity of the flexibility, and with variable stiffness actuation. Okay, so there are all the combination. So the application is exactly what I wanted. So in rigid robot, we work in the zero gravity field, so gravity is always compensated. And this is useful also for designing reflex slow to collision, which are torque-based. And then also for regulation tasks, actually. So without caring about human-robot interaction, just we want to go from one point to the other and do it with good transient. Not only being asymptotically stable, we would like really to have less oscillation and so on. And when we tune the gains in this case, the presence of gravity is disturbing. So if we can remove gravity exactly from the variables that we want to control in the transient motion, then we would be have a much easier task in order to tune our controller. So I don't know if I'm going to go into the detail of this, but I have 3 slides which pictorially shows what is the problem. So let's start with the easy case. We have a rigid robot, rigid in the links and in the joints, under the action of gravity. This is the model. So we have to design tau, and when we apply tau, there's some motion of the link variable q. This is the situation under gravity. Now we would like to design this so that the system behave as if it was on a horizontal plane. The variables are the same, but their evolution is labeled q0, to remember that there's 0 gravity here. And after we have done something here to eliminate the presence of g, then the remaining part here is tau 0. Okay? Or vice versa. If you have this system and then you apply a torque tau 0, whatever you want, computed torque, PD, PID, whatever, and you have some motion q0, you would like to have the same behavior of q0 here despite the presence of gravity. Now, it seems it's a trivial problem, in fact, but we need to formulate it correctly because later on one may get confused. And in fact, the solution is trivial. So the tau here is just the tau 0, that the residual torque used for doing what you want to do on the robot without gravity, plus tau g. And tau g is exactly canceling this. Okay? And the evolution of q will be exactly the evolution of q0, because at this point, this removes this, and this system is moving physically under gravity, but in fact only under tau 0. This is without gravity and moving again under the same torque. Okay, so q will be equal to q0. Okay, and this is due to the fact that we have full actuation, so each degree of freedom is actuated, and we have collocation of the applied torque with the gravity acting on the system. So this is the result, and then you can do whatever. So let's consider now flexible joint robots. So elasticity in particular. So we have torque tau applied by the motors. This will modify theta. Theta will compress or exchange some potential energy, so we'll later on move also the link motion. This is just 3 link, just for representing things, q1, q2, and q3. And this is under gravity, and this is the full model. You see that there is no collocation between these terms that you would like to cancel and this term here. So you would like to do exactly the same, so to let this system design a tau here so that this system behaves like this system where gravity is not there, so it's on the horizontal plane. And when you apply tau 0 here, then you will have some motion of the motor position and then some motion of the link position, and we label 0 this quantity. Okay? So here we have non-collocation, as mentioned. And tau here will be designed, again, applying this tau 0, like if the gravity was not there, but we need to design this tau g. And this cannot be just simply this tau. We may guess, we may say, okay, just even if this term is here, let's put here g of q inside the expression of tau. And let's see if this works so that we have consistency of the position of the links, not of the motor, all the time with respect to the model which is not loaded by gravity. I don't know if I'm confusing things, but I hope it's clear enough. And of course, the same thing happens if we have variable stiffness actuation. Here I'm talking about antagonistic situations, so we have two equal motor for each joint. So tau 1 and tau 2, they move the motor position theta 1 and theta 2, and they interact in a coupled way in moving the links and in changing the stiffness. Okay? And everything happens under the action of gravity. So this is the multi-degrees of freedom model in presence of gravity and with antagonistic VSA devices. So this should behave, again, like this with all zeros. And now we would like to design tau 1 and tau 2, if possible, so that not only the Qs behave like the Q0 of the unloaded case, but also the stiffness of this device behave like the stiffness of this device, which is not under the permanent action of gravity. Okay? So how do we solve the problem? We solve the problem by the principle of feedback equivalent. We know that if a system is feedback linearizable, is equivalent to some linear system. So the concept is very simple. I have, let's say, consider the joint elastic case. I know that the joint elastic case, there is a controller that will put the system into chain of 4 integrator. And if I have the same original system, but without gravity, there will be another controller that brings the system to the same chain of 4 integrator. So they are feedback equivalent to the same system. And this is what this represents. No? We have a gravity-loaded system. There is some static feedback and change of coordinate in general, so that in the right coordinate, the linearizing coordinate, I see a linear controllable system. And then there's a gravity-free system, and there will be, if this is feedback linearizable, there will be another controller using the state of this system, and another change of coordinate T0, which brings into the same linear controllable system. Okay? Now, of course, this is a passage. If I'm combining things and optimizing, I can go from one way to the other, and the one way to the other is this one. No? So I'm applying some input to the gravity-loaded system so that this behaves in the right coordinates like the gravity-free. Not all the variables, but at least some variable, the linearizing output. So I need to check if those systems are feedback linearizable. And we know already that systems like this are feedback linearizable, and the linearizing output, those variables that can be matched, are exactly the link position with relative degree 4, because I have to take the derivative 4 times in order to invert the system. Now, all these robots using these different types of VSA, well, they're all perform in the same way, although the mathematics is different. So I have, as a linearizing output, exactly the position and the stiffness, this with relative degree 4 and this with relative degree 2. So I can solve the problem. And in fact, I just show this for the easiest case, which is the elastic joint case. Then we have a case where this is nonlinear, but there is only one motor, and then the variable stiffness case. So this is the situation. Here I'm including also some damping on the motor side and on the link side, not some viscoelastic damping of the spring. Pay attention, because this will perturb the result. So this is what I require, so that the Qt behaves like the Q0 of a system where gravity is not there. Okay? And if I do the computation, here is the additional torque that I need to apply. Not only the cancellation of gravity, this is the things that may surprise, but includes the first and second derivative of g. Okay? And you can do this analytically or numerically, whatever you. Of course, as k goes to infinity, those terms are not important, and in fact, you recover the rigid case. Okay? If these are negligible, you don't need to compute the first derivative, you just jump to the second derivative of g, and so on and so on. This is just one joint. It's a very simple simulation that shows that this is the behavior. Okay, here you see the red line, and then there's a black line which is fully superposed, which is exactly what we obtained for the unloaded system and the loaded system, but with a controller that cancel things. And you may wonder if things depends only on the static part. So if you just apply g of q, and not the derivative first and second, if you get more or less the same results. And this graph is just the comparison between the gravity and non-gravity. And first of all, you see that the motor of the two systems, the loaded system for gravity and the system, let's say the model, which has no gravity at all, of course the motor behaves differently. So we cannot impose the same behavior. It's the link that behaves the same, the linearizing output, but not the internal motor. While here, you see the evolution if you're using the right TG, so with G of Q and with the derivative first and second, or just compensate, let's say it's not static, but you can call it statically, G of Q. And you see that there's a difference of the order here of, let's say, 2 Newton meter over 10, so 20% is due to the fact that you're really correcting things. So you may be satisfied even with this error, but if you want to do things exactly, you have the expression of your desired controller. This is the variable stiffness case, and you will see that it's much more involved in this case. So same thing, you want to both have the stiffness and the position of Q behave as the system was not having this G of Q acting on it. Okay, so you're imposing that Qt, which is the actual system, behaves exactly as the unloaded Q0, and that sigma t, the actual total stiffness of the device, behave exactly like the stiffness of the unloaded system under the action of some torque, which you will apply to both systems anyway. And okay, this is the expression of the torque. You see it's much more involved, at least graphically. And in fact, it's not even a closed form solution because you have to solve those nonlinear equations. It's only for special expression of the joint elastic torque and the profile of sigma, like quadratic case, you can solve this analytically. Otherwise, you have to solve it numerically. And the actual behavior is like having this. This is the VSA under gravity. It's a CAD representation, so this is the link. So these are the quantities that produce sigma and whatever. So via feedback is like twisting this over and have gravity cancelled, okay? On the action, on the motion of the link. Of course, you can imagine that when I'm moving this and it moves exactly like this, the loading of the two transmission and the torque associated to this will be different from this case. It's not the 3 cards game, no, that you just let gravity disappear. Gravity will be focused on only one part of the system, while the things under control behaves as desired. And here, for instance, this is the situation, open loop torque in absence of gravity. So this is the tau 0, okay, the 2 tau 0. And in order to reproduce exactly the same behavior of the link, so going up and down, or having this transient of stiffness, this is the torque that you have to apply, the total torque that you have to apply to the loaded system, so which is clearly different from that, but you obtain the same behavior for those variables. I think that I can skip this. And in fact, these results led us to design a nonlinear PD controller, which is capable to obtain regulation globally with no requirement on the lowest stiffness of the device and on the lowest gain of the proportional term. Why? Because we removed gravity from the quantity that we wanted to control. And so we are exactly as if gravity was not there situation. And this is the controller, whatever. Okay, I can skip that. So in the last 10 minutes, if you sustain me, I can just show some results on collision. And I will be very briefly, because this is known material, but just to show you the passage. No? In all my presentation, I'm always referring what happened in the rigid case, then in the elastic case, then in the variable stiffness case. So again here, we started in 2005, 2004 actually, to work on this problem. So a rigid robot with some control torque, whatever, open loop, PD, computed torque, you don't care. And then sometimes you have an extra torque, tau k, which is a joint torque caused by a link collision. So you know that this torque is generated like this with some generalized force and momentum acting somewhere in the structure, and with the associated contact Jacobian generating these quantities. But you don't know these quantities, you don't know where the contact is, you don't know the intensity, you don't know anything. You know the model. Okay? So this was the situation, and you can model this situation like a system fault. Actually, we were working on actuation fault detection before, and we realized that this could be used also in this context. And the main idea, well, we had several variants, so using the total energy for just detection, or using the generalized momentum of the system, and monitoring the generalized momentum. Why is that? Because the generalized momentum has a nice property. If you write down the dynamics, it's a first order dynamics, and you will see that here there's no inertia matrix. So each component of P is affected only by the total torque acting on the right-hand side. One part of this torque is known because it's the torque applied by the motor. The residual part is exactly what is caused by the collision. So by monitoring P in a proper way, you can not only detect, because you can detect also with a simple total energy, a scalar signal that can be built but while monitoring E, and if this scalar is 0, there is no contact. If this happens to become different from 0, and over a threshold, let's say due to noise and uncertainty, then you have collision. But you don't know where this collision happened. While with this momentum and with the residual, vector residual built upon that, we have a lot of information on where the contact occurs, and then we can react to this contact in a safe way so that to abandon the collision area. So the system is like this. We have a permanent collision monitor that detects and isolates. So sigma is a scalar which monitors the total energy, and R is the residual vector that monitors the evolution of the generalized momentum. You have some threshold, then you recognize a collision, and then you can react, deactivating what the robot was doing, and then providing the reaction torque so that in response to some collision with it, you don't know where. There's no extra sensor, there's no Kinect, no tactile sensing in this situation. And moreover, once this residual returns to 0, that means that you don't have any more contact, so you can reactivate your original operation. Or if you are reacting to a collision, so you have a reaction strategy, these signals are still on, so you continue to monitor things. So if you have a collision here, and then while retracting from this collision, you have another collision here, you react also to this, and so on and so on. It's like a robot moving in an artificial potential field, so being repulsed by obstacles, only that this is not artificial, it's real, because there are forces applied to the system. Okay, so I skip this. So this is the form of the residual vector, something that you can compute based on the model. No mystery, just Q and Q dot, this strange transpose of the factorization matrix of the Coriolis and centrifugal, the applied torque or the current. Here everything is rigid, so. And then the evolution of this vector is that of a linear, decoupled, stable first order filter. So when this goes back to 0, this means that this is no longer present. Otherwise, it reacts as a filtered version of the joint torque resulting from the contact, whatever this contact is. Okay, I will skip also this, and then there are reactions. Okay, so this is for the rigid case. Now, we never did experiment on a rigid robot where we had the dynamic model and we had access to all these things. The first experiments were made on the DLR lightweight robot, this one, the DLR3, where we had joint elasticity. So again, this method applies to the joint elastic case, not only applies to the joint elastic case, but has also a nice feature that it applies as such, only replacing the applied torque to the motor with the measured torque that the joint torque sensor is providing to you. This is one way for implementing exactly the same algorithm. So this is the model that we have discussed before. Tau j are k times theta minus q, but in fact they are directly sensed. No? So in fact we are measuring theta and tau j, and from this reconstructing q, and q is used inside here. Okay? And then we use exactly the same formula as in the rigid case. Pay attention. The only difference is that instead of having tau here, you have tau j. So instead of using in the computation the applied torque from your controller that you know in advance, you're using in the computation the measured tau j from the joint torque sensor. And in fact, this is the expression of the residual. I label it elastic joint because it's exactly the same as before, only with tau j in place of tau. Okay? Let's skip this. Of course, we need zero gravity, and just to have an idea of the behavior of these are 2006 videos. So here not only we recognize, but also we have some reaction. This is admittance mode. So based on the residual vector, he stops and then he applies some velocity at the joints, which is proportional to this residual. So it's proportional to the estimate of the joint torques acting on the joints because I'm touching the robot here and there. I don't like this admittance mode strategy too much. I like this reflex torque, as I called it, because this is much more smoother. Okay? And in fact, it's very friendly. And I remember that day that everybody in the lab wanted to play with the lightweight robot. And of course, you can also have a first impact at 90 degrees. Of course, you have seen this robot is moving, doing his test. Then there's detection and reaction, not just stopping the robot. This is the elementary reaction. What EVA is implementing is exactly this method. Only that they have detection, but they don't make any reaction because they don't feel confident on that. So the most simple reaction they can do is just stop the robot. Okay? But other than that, is exactly this method implemented. So here, the robot is coming against me at much higher speed, but again, and you're certainly familiar with all the video by Sami Ad-Din with the knife and the pork and hitting the head and so on. This was all implemented in the joint elastic case. So what can you do for the variable stiffness? Well, you can do more or less the same thing, but here we had another idea. Since one of the problems of the variable stiffness is that the stiffness itself is changing. It's changing in real time because you can control and so on, and you don't have a direct measure of that. This is why you will hear on Tuesday also a talk by Fabrizio Flacco on estimation of real-time online estimation of stiffness in variable stiffness devices. So you would like to get rid of this. And how you do this? Well, you just modify the way in which you compute the generalized momentum. So instead of computing the total momentum, you're adding the momentum due to the motion of the link and the momentum due to the motion of the two motors. Okay? So if you write down the time derivative of this expression, this is the single link case, but exactly the same applies to the multi-link case. And you can build up this residual, a scalar in this case because it's just one joint. Then the evolution of this will exactly be that of a filter, first order filter, driven by the unknown collision torque tau k. So you start with R0 and this remains as 0. As long as this does not change, then R dot will change, so the R signal that you are computing will drift from 0. When you remove this, because of the stable filter situation, it will recover exponentially to 0. So that you can also recognize that there is no longer a contact. Okay? And in this expression, there is no information about the stiffness of the joint. So we remove this by just combining the component of the generalized momentum from the motor side and the link side. And I will skip this. There are also reactions, but okay, this is the multi-degree of freedom version. As long as this model applies in the end of case, and by the way, this model applies exactly if the assumption A4 of Spong holds for the joint elastic case. So if you neglect in the kinetic energy, in the angular part of the kinetic energy of the two motors of your variable stiffness device in this antagonistic case, if you neglect the part which is due to the fact that the motor are rotated around by the previous links, which again is a very reasonable assumption, then you can extend the one DOF case to the multi-DOF case and nothing changes. So for instance, these now are all vectors. You see that this is the momentum of the link side. These are the two momentums summed up of the motor side with diagonal inertia matrix. This is the expression of your residual, and you see that there is no information on tau j ever entering here. There are the two applied torque that you're using. So if you're using here PD or nonlinear feedback, you have to put exactly what you're commanding to your motor here, or the current that you're commanding with a factor of scale, inside this expression of the residual, and everything will work. In fact, this is and this is the last slide. This is Nico Mansfeld from DLR trying the method on the DLR hand arm system, which is driven by their BSI devices. It's called hazy because it's hand arm system, I would say. And you see that this was the first experiment by Nico, so he's a bit scared at the beginning, but okay. And here there's no reaction, just stopping. So the same concept as I showed, and this was my intention, moves from the rigid to the joint elastic case to the variable stiffness case, even in the multi-DOF situation. Okay, so from 6 o'clock today, enjoy Rome. Huh?